Okay, our problem is 18, tack 11. We have a problem with a diving board. Man rotating from 0 degrees to 90 degrees. When he reaches 90 degrees, he loses contact with the board at point A, falls 30 feet, and hits the water. This is center of gravity. His radius from point A to the center of gravity is 1.5 feet. We're also given the radius of gyration is 1.2 feet. The weight of the man is 150 pounds. He rotates about point A until he loses contact with the diving board at theta equal to 90 degrees. Problem asks, if he stays rigid, determine how many revolutions he makes before striking the water. The steps to our problem, as with all statics, dynamics, strength materials problems, we're going to start out with a free body diagram, analyze that. We're going to move to conservation of energy. We're going to find the angular velocity from that. Then, assuming that the angular acceleration is 0 due to him staying rigid, we're then going to move to kinetics, find the time t that it takes for the man to hit the water. Use that time to find out how many rotations using angular kinetics. Here we have the free body diagram. Starting at 0, theta equals 0, then analyzing the man, the reaction at A on the board. Once theta, he has rotated 90 degrees. The reaction at A goes to 0. So we can completely disregard the reaction at A once he finishes his rotation about the board. So our second step is the conservation of energy. We're going to have our initial kinetic energy plus the potential energy equaling the secondary kinetic energy. From the equation we know that our initial kinetic energy is going to be equal to 0. Our change in potential energy is going to be relative to the change in height, which is going to be right here. We're going to have G is going to change height by 1.5 feet. Setting this as our datum. So that's going to be 150 pounds times 1.5 feet. Our second kinetic energy is going to be equal to 1/2 times the mass times velocity squared plus 1/2 times the moment of inertia times omega squared. Now our V right here, using translational velocity, we're going to set that equal to rotational velocity crossed with the radius, and that's going to end up being 1.5 times omega. And then solving for our moment of inertia, we're going to have mass times the radius of gyration squared. So that's going to come out to 150 divided by the acceleration of gravity times 1.2 squared. Setting all that, putting all that information into our equation for T2, we're going to find 1/2 times 150 divided into 32.2. We're going to have this right here plugged in for our V, plus 1/2, 150 divided by 32.2, 1.2 omega, all of this squared and all of that squared. Solving this for omega, we're going to get this 8.59 angular velocity squared. Plugging this back into this equation, we have our 150 times 1.5, which is our potential energy, equaling to our secondary potential energy. Our initial kinetic energy is going to be equal to 0, so our secondary kinetic energy. Solving this equation for omega, we're going to get 5.12 radians per second. So our third step is going to involve kinematics. So we're first going to have to solve for the distance traveled downward. So we're going to have y equaling to y naught plus v naught times t plus 1/2 acceleration naught times t squared. This is going to go to 0, since our datum is at the edge of the diving board at point A. So he's going to travel 30 feet down, and then plugging what we got for omega, the angular velocity, back into this equation, we're going to solve for v naught. So omega from our previous equation was 5.12. We're going to multiply that by the radius, which is 1.5. That's going to give us 7.68 feet per second. So 7.68 feet per second times the time, which is what we were trying to find, plus 1/2, 32.2 feet per second squared, gravity, times t squared. So this becomes a quadratic equation problem. We're going to solve for t, and t ends up, we get a positive and a negative root. We're obviously going to take the positive root. This is our positive root. T ends up equaling 1.147 seconds. That's how long it's going to take him to fall 30 feet. Now in that time that it's going to take him to fall 30 feet, he's going to be rotating. So this is the last equation of the problem. We're going to find, using rotational kinematics, I'm going to find that theta equals to theta naught, which goes to 0, since he starts from 90 degrees and hasn't rotated at all yet, plus omega naught times t plus 1/2. We said again that we assumed that the acceleration, the angular acceleration, is going to equal to 0 since he's staying rigid. So this right here is just going to go to 0. So it's simply theta equals omega naught, which we found is 5.12, times t, which we found up here, 1.147 seconds. And the seconds are going to cancel out, so all we're going to get is radians. So our theta, we get 5.87 radians. So that's how many radians he's going to travel. To find how many revolutions he actually experiences, we're going to plug this into, we're going to basically divide our answer for theta, divide that by 2 pi, which would be one full revolution, and that comes out to 0.934 revolutions. So he doesn't even make quite a full revolution during that time. So almost one full revolution. And that's the end of our problem. So back to our initial problem. Our man rotating about point A, falling 30 feet. It's going to take a little over 1 second for him to fall 30 feet.
How many rotations does he make?
He's going to be making just under one full revolution, 0.934 revolutions.
Oh, word.
And once he hits this sweet, gorgeous pool, what he doesn't know is that there is a megalodon fish shark in here about to kill him. So he ends up dying in the end, so maybe he shouldn't have dove off the diving board in the first place.